So in chapter 19, we're talking about process control, and that's our main goal in this chapter. There are some additional areas that I want you to be involved to understand a little bit, and that's what we're going to talk about tonight. And there's three other areas I would like to talk to you about a little bit, and two of them have to do with what we were talking about before, and another one is programming of the PID block in the manual mode. So those things we want to cover tonight in this chapter, and we want to get into chapter 20 on safety, just a little bit if we have time. So I know that a lot of this stuff is kind of foreign to you, and you've never seen it before, but if you look at this and you look at it well, it makes sense to be able to write a program that relies on these blocks. And if you remember from the other night, we wanted to look at a series of like a PNID drawing and find where the PID blocks were. And anytime you had a C as a third character, that tipped you off that was a PID block. Okay, so that's main important thing for you to be able to translate. And this will be obviously something that you would you might think this is trivial, that this would be this, but in a sense, it does get you started down the path of writing this program. And that's basically what you want to be able to do. You want to be able to write the program to get this to work, and after you've got it working in auto, then go back and start adding some of the other components to it, some of the other parts that you'd want to add. Okay, and basically those kind of things are the auto and a manual mode, and I want to go back and I want to talk to you just a little bit about that. So in this case, some of the things that you can do are in most cases, what you want to do is you want to fall back to a safe state. And let's just talk about some of these states, okay? So here is a state where you are looking at, instead of one temperature, you're looking at 3 temperatures or 5 temperatures or whatever, and I've got the wrong color. I got to go back and change my color. But anyway, I want to have, I talked to you before about only one eye, and I want to hedge my bets, and this is a case in point where you want to hedge your bets, and you say, okay, across the crown of a furnace, instead of having just one temperature thermocouple up here, I want to have 3. I want to have one over here, one over here, and one over here. Or maybe I want to have 5. Maybe I want to have 10. I don't care. But at least I want to hedge my bets, and I don't want to just have all my eggs in one basket and read all my temperature out of 1. I want to read it out of like 3 or maybe 5 or whatever. So basically, you have a weight times each of your temperatures, and you add those up, and that has to add up to your final temperature that you're going to feed into your PID block. Okay, but your weights have to add to 100%. So if one is 30 and one is 40, the other would have to be 30 to get up to 100, or else you do not have a correct proportion. So basically, if this does not add to 100, what do? We have no choice. If it doesn't add to 100, if it's not equal to 100%, you must go to manual. Slam it into manual and wait until they get the 100%, and then you put it back in auto, and then it works. Okay, so this is something that you say, well, that's kind of an odd thing to do. But on the other hand, if they can't add to 100, you don't want them putting that number in there. You want them basically to only put numbers in there that are give you a 100%. Okay. Now, an aside about something like this is that once you put these in and program this, there is a process engineer who basically will tell you to go. They don't want you to know what they run as percentages. These are called profiles. And everybody has their own profile. Somebody wants to run 30, 40, 30. Somebody else wants to run 25, 50, 25. I don't care. I don't think any of you care really, but maybe some of you do. But the people that are running the show like to put their own profile in. And from shift to shift, they might come in and one person might put in one profile, another person might put in another. It's weird how they protect their little kingdoms of what these profiles are, but that's what they do. And they basically, they don't want you to know what their profiles are. And that's one of the things that you think, well, that's kind of odd, but that gives you some flexibility. That gives that person some flexibility as to how they run their process, and that's what you can do. Okay, and that's a case in point of putting it into manual if they don't add up to 100%. Now there's others as well. There's quite a few of these, but you can see that if you want to run an auto, you have to be able to guarantee that it's going to run correctly. Okay, and that's one case. Okay, so anti-reset windup is the situation where you have an error, and it's like winding a watch over and over and over. You get it really tight, and the integral of the error becomes very, very, very high. And when you release the error, it takes forever for it to come back to stability. Another thing about this is when you go from mode to mode, you want to have what they call it's a I forget. No, I don't forget, but it's auto bump. It's called bumpless transfer. Okay, so bumpless transfer is a situation in where when you're working from one mode to another. When you're going from one mode to another, okay, and when you're going from one mode to the other, you don't want the system to do this kind of thing or do this kind of thing. You want it to go flat, or you want it to stay. This is what you want right there. So what you have to do is on a change of mode, you do a one shot that actually moves the information from the prior mode to the present mode. Okay, and that can be from cascade to local in auto. It can be from auto to manual. It can be from anything to anything, but you definitely do not want to have a kawonk or a kawonk. You want to be, this is what you want right there. So bumpless transfer is an exercise in using a one shot when you change modes to keep the system stable. And this is programming. This is something that you have to program. All right. Now, if you were to use a DCS system, many of them have just a checkbox that says, do you want bumpless transfer? And you say yes. But if it's a PLC, you have to physically program it in using one-shots. So that's an example of having to use a one-shot on a leading edge of you move something in. And non-standard modes are what I talked about the other night about what we call something like control output tracking, in which you have a mode in which you're saying, I'm within an area and I'm starting my system up, and I want to stay in this area right in here. I don't want to go out here and I don't want to go up here. But when you're starting up and you're in the first part of a startup system, you're really in manual. Okay, until you get up to a certain position, you're in manual. But you don't want them to know that you're in manual. You basically say, this looks like auto, but it really isn't. and you're actually turning the thing up in manual. So it's really a lie to say it's an auto control output tracking. It's an auto mode. It is not. It's a manual mode, but it's in the lower range of your control, and you want to start up from a 0 to a certain percentage, maybe 50%, 40%, with this thing called control output tracking, which really is a manual mode. So again, there are different modes, and some of them you have to program, some of them you don't, but this is one that you probably, if it's a PLC, you'll have to program. Okay, enough on that. Okay, so now you've got a little bit of what it takes to go from auto to manual, manual to auto. In the case of Allen Bradley, it's a bit. The auto manual bit is a bit. It's just one bit. In Siemens, they have like 8 modes. Okay? Don't be surprised with Siemens. They've always got more than you can ever imagine. 3 is auto, 4 is manual, and I don't care what the rest of them are. I don't remember them. I do remember these because if you're an auto, you slam it in, put the number 3 in for the state. If it's manual, you put it in 4. That's all I remember, but I do remember those too. So again, it's a number. Here it's just a bit. But you can see that Siemens always does something a little bit more. I don't know why they do, but they do. So again, that's help, huh? Anyway. So this is, and building a ramp block, another feature is if you need to go from one set point to another. So here you're sitting here and you've got like, you're running a zone and you've got, here's your temperature PID. And here's your gas and your air or oxygen, either one. And let's say you're going from set point 1 to set point 2. You very, very, very rarely do a step function. This is almost never used. What you do is you ramp it to that block, ramp it to there. Why is that? Because this can cause instability, where this is very easily, you can keep this very stable. So a ramp block is much preferred, and you might have to build a ramp block. Okay? We've talked about it, how to build one before, but it's fairly straightforward to build. It's a timer and an adder is all it is. This is a ramp block, believe it or not. Or this is going up, this is going down. This is ramping up, this is ramping down. I was building the project at Algoma the first time I did one up for them, and the fellow came in and told me, he says, I want a ramp block in front of every PID block. In other words, I want a ramp block in front of every one of these systems like this. So I went back, put these in. Didn't take very long. It's not a big deal, but it is something that you may have to do. Make ramp blocks to go from set point to set point. Okay. So this is the one I talked to you about on the without the delay, and this is the one with the delay. This is a lag block. We talked about this. This is our cross-limiting effect. And this is one we talked about. This is called feed-forward control. Basically, it's a jump of a value for your set point if something weird happens. And the output of that is this. Instead of having to climb up a hill very slowly, like doing something like this, right here, instead of doing this, what you do with that output is you jump immediately to the output that you know it's going to be at, and now you're stable again. So basically, you go to manual, put the new response in, and then go back into auto, and now you're in auto again, as opposed to having to do this. This takes forever, and it leads to instability, and that's why they don't like to do this. They put it in manual, go to a new output, and then you put it back on auto and let it run again. Anyway, enough on that, and hopefully everybody got a little bit of their information from this area. Wonder how many of you did ChatGPT to do that? I don't need to know, but I wonder how ChatGPT does with PNID drawings. I do not know. Well, anyway, so this is pretty much it, except for one more thing, and I want you to go down here and I want you to see this, because this is we're getting through this gradually, very gradually, but we're getting through. By the way, how many of you know anything about Visio? Visio is a drawing package that is very useful, and it is on some of the computers in some of the labs that we have here at the university, and it does P and ID drawings. You can do a number of things, including P and IDs, and this is some of the symbology for P and ID drawings. Okay, now we have also a problem. This is a test problem, and this is a good one in that you may see here is an equation, right? Right there is an equation, okay? So if you are operating only in the proportional and the integral realm, no derivative term, okay? If you're doing this, what is the output? The output is the CV, okay? The output is the CV. It's called the control variable. That's the output as a control variable. And if you can understand what is going on here, you can actually predict what this formula is going to be doing, okay? So what if I give you this variable and this variable and this variable, can you, and this graph, can you graph the output? This is the error. Can you graph the output? And you should be able to do that, okay? And the reason for this is if you have never looked at a PID controller before and you say, what is going on here? You will be able to see what the output is doing based on this error. And you'll see, and thank you, Professor Evans, I didn't put the derivative, the delta, the derivative one in. The derivative one is messy, but the proportional and the integral one are not so bad. So if you look at this and you say, okay, now what is he trying to ask here? So the P term is 0.6, and the action, the integral action, or the I term is 0.6 as well, okay? Initial value of 0.15%, okay, V0 is 15%. And this is in percent. No? No, this is actual error and numbers. And then you want to graph, the goal here is to graph the output, or the CV. Okay? So it's in percent. And it starts at 15%. And does it go up or go down? Well, let's just figure out what it is doing here. So at t equals 0, it'd be 15%. Then as you go up from that point, let's see, No, it's not 15%. It's 15% plus, okay, so it isn't 15%. It's V0. So before it came in, before it got to this point, it was 15%, but we don't know what the error is now. We know coming in it was 15%, but we don't know what it is now. So this was prior to t equals 0, it was 15%, okay? We don't know what it is right now. So let's look at it. Let's see what it was. So let's just look at it and see at t equals 0, what do we have? We have an error of 1, so it's 0.6 times 1, and that is it because there is no integral of the error. There is no anything under the curve, there's no integral of the error term. So it's 0.6 times 1 plus 15, or 15.6. So it jumps to 15.6 at t equals 0. Does everybody see that? So at t equals 0, it jumps from 15 to 15.6. Okay? Then at t equals 4, we have an error of 2. So it's equal to 15% plus, or 15, plus 0.6 times 2, which would be this term, plus 0.6 times 0.6, which is this term, times the integral of the error. And what is the integral of the error? Well, there is an under the graph, this is the integral of the error. So there'd be 4, if you just count this across here, this would be 4, and this would be another 4, but it's a triangle, so it would be 2. So it would be, integral of the error is 0.6 times 0.6 times 6. Any questions about that? So the integral of the error, so at t equals 0, the output CV is equal to 15.6. At t equals 4, it's 15% plus 0.6 times 2 plus 0.6 times 0.6 times 6, which is equal to a number, and I'm not going to figure out what that number is, but there you go. That's how you do it. Now, at the next point that you would calculate is maybe down here. And now you have minus 1. So at 7, at t equals 7, we are at what? We are at minus 1. So it's 15%. Minus 1 times 0.6 plus, now what's the integral of the error all the way over to here? Well, this little piece cancel each other out. So that there is nothing there. And this was 6 plus another 1 plus another 1/2, so it's 6 plus 1 plus 1/2, so it's 7.5. 7.5 times 0.6 times 0.6, which is equal to a number. Now you can figure out what the output is at t equals 7. Okay? And then you can go to 10, and you can do the same thing. And now you have 7.5 minus 1, 2, 3. So you have 7.5 minus 3, or 4.5. So at t equals 10, you have 15% minus 1 times 0.6 plus 4.5 times 0.6 times 0.6, which is equal to something else, and I don't know what that is. Okay, and that's at that, and then at 12, we have 15 minus 0, because we went back to 0, plus 0 for my proportional term times 0.6, plus 4.5, and then we go 2 and we go 1, but it's a half of that because it's a triangle, so minus 1, so plus 3.5 times 0.6 times 0.6, and that is equal to my value at t equals 12. And you graph that out, and you've got your graph, whatever those numbers are. So you got 15 minus 0.6 plus 7.5 times 0.6 times 0.6. That is my number at 7. And you can do this. This is very doable, okay? But what that does is this. It actually makes you look at how this proportional integral controller is actually making adjustments as you go along. If you understand how to do this, you'll never not understand how a PID controller is actually working as it's crunching up and doing what it's doing. So I'm asking you to be able to graph the output, CV. Any questions anybody's got? I went through this kind of fast, but does anybody have any questions about how this is done? Hopefully not, but it's a way of understanding how a PID algorithm actually works. If you can understand this algorithm right here, plus the derivative, if there's a derivative term, but I drop out the derivative because it gets a little bit more difficult to figure that part of it out. But if you can graph the output based on the error going up or going down or going, and now again, I don't know what the tuning parameters are for this controller. I don't care. I just graph the output and show the integral of the error and then whatever it's doing, and then you can see that it can control, okay? So I'm actually doing this here. So if you can see this, I'm actually doing this. There's another one. Okay, again, I don't want to get into the arguments between those who like PLCs and those who like DCS systems, but there are some of the arguments against PLCs and for DCS systems. And you can figure it out very quickly that they want you to buy a DCS system. And I'm just pointing out that here's another comparison of DCS and PLC systems. And you're going to find people on both sides of the fence. This is not like, this is not Chevrolet and Ford. This is more of some people prefer one and they've got their reasons and they're very adamant about them. You're going to run into both sides. And again, to convince somebody that you can do a DCS system after all you've ever programmed has been a PLC system, it's a little bit of a stretch, but you can remind them that PLC systems have FBD, functional block diagram, and many of the DCS systems, they look very, very, very similar to FBD. So you can say, yeah, but I programmed an FBD and I understand the differences and blah, 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 and all that kind of stuff. But they are not that different, other than the fact that PLC systems tend to be less expensive. And if you've never watched RealPAR's videos, they are some of the best videos out there on some of this stuff. And if you walk into an environment where you're actually doing this, some of the RealPARs is really, really, really good. And I don't have time to go through some of these, but these are very, very, very good videos. Okay, any questions about chapter 19? It's pretty much in the book as far as I'm concerned, and there's enough there. Oh, and by the way, what's your assignment this coming week going to be? You can almost predict it, but it'll be one like the ones back here where you are being asked to one of these. Use variables and write the auto program in the PLC for the PID. In other words, find all the something C's and find the PV, the SP, and the CV, and be able to figure those out. Okay, so it's basically we'll find one of these. We'll get you one of these, and I'll take my book, open to a page, and find a P and ID and show it to you and be able to write the blocks that show the PID blocks of that. And I want you to be able to do that. It's not like there's nothing magical about it. It's just, there's another one and there's more and there's more and there's more. I've got, you saw the pages of those and, there's a lot of them. So again, I want you to understand that this is not rocket science. It's just finding the something C bubbles and then trying to place together and figure them out. And you're almost to the level of being able to program a full PID process by doing that. But I don't want you to get too confident. But on the other hand, you're close. You're very close to being able to do that when you've done this. Okay, chapter number 20. I want to talk about chapter number 20 in the sense of this is I hate to brag about something, but this is not a chapter that you're going to find in most books, because it takes a lot of digging to get to this point, and there are just not a lot of the people that are out there that are actually doing this kind of thing. And it's been a couple years since I put this stuff together in this chapter. As a matter of fact, it's been about 4 or 5 years ago since I put this all together, but I really struggled to get this to this level. But we have 8 of these PLCs, and I honestly, I invite you to, and it's an 8-point lab to be able to wire this thing up, and I really encourage you to do that if you want to. It's hate to use the word fun. It's very different, but it's very doable. And anyway, I like for you to think that this is something that most people don't get. Okay, so what is it about well, I don't want to make it sound like I'm prejudiced against Allen Bradley, but what are 2 of the major differences between Allen Bradley and Siemens? One is networking, and one is safety, okay? So the safety aspect of Allen Bradley, and it came along because the United States was late to the game in safety, all right? Having a safe PLC was not something that we considered as doable for a long time. And the reason for that is because we just didn't want to have safety in the PLC. They resisted it for a long time. And I've got it someplace down here. I have a timeline of when safety was, right here. So up until year 2003, we did not in the United States allow safety in a PLC, okay? You had to bring the safety in from outside, and then you could do everything else in the PLC, but you couldn't do safety in a PLC, all right? So in 2003, the wall came down, and it was allowed in the United States. Now, who was the guru that in 2003 allowed this and hadn't allowed it up until then? I don't know. But all of a sudden, in the United States, in the year 2003, we allowed safety in the United States. Now, they had done this in PLCs in Europe for years and years and years and years and years, and that's why Siemens is ahead in this arena, because they were doing it for so many years, okay? But this is an idea of, whoops, we were behind, and we really were behind. And I hate to emphasize it too much, and I know Allen Bradley's got a good brand and all that sort of thing, but basically they've always been kind of sucking air. They've always been kind of behind on this area. Now, what do I mean by safety? Well, if I were to take get on board a rocket ship to go to the moon, I would want what we call TMR. What does TMR stand for? It stands for triple modular redundancy, okay? In that case, you have 3 computers, okay? You got 3 guys. You got three of them running the system. And if this one says it's a 1, and this one says it's a 1, and this one says it's a 1, you're good. If 2 out of the 3 of them says it's a 1 and the one says it's 0, you can still fly because you have a voter system, and any 3 out of 3 or even any 2 out of 3 will get you to a destination. Okay? You can have one failure in a TMR and still go along. Okay, that's called triple modular redundancy, but that's a lot of dollars. You can spend a lot of money on TMR. But in the case of human life, in the case of, not wanting to have a problem with going to the moon or whatever we do, that TMR is well worth it. But in a factory, it's not. So what you do in a factory is you have 2 systems, an A and a B, and if they agree, you go, and if you don't agree, if they're both a 1 or both a 0, if they agree, then you go. If they don't agree, then you shut down. Okay? Does that make sense? You shut down if they don't agree. So this is kind of a philosophy of, this is called fail safe. This is called fault tolerant. This is called fail safe. The difference is a lot of dollars. But these still are more money than a typical PLC. Okay, now I want to talk about a specific example and how this has gone through the years. Okay? So I have a picture down here of a press. Okay? So in some presses, they were at one time allowing you to put the left and the right buttons, which were the buttons that you have to hold your fingers on these buttons for the press to come down. Now, there were presses that were never allowed to do this with a PLC, and then there were ones that allowed you to do this with a PLC, okay? I've worked on both kinds, but the ones that would allow you to come down were the pneumatic, the air presses that would allow you to come down. And I did these for a company here in Toledo, and the early ones we actually wrote that you could press one and then the other within a certain time period, and if you got them both down, you would allow it was a hood liner press. It was just pressing down and making a hood liner is all it was. Okay, and it would come down, press that, then go back up. Now, later on, they came along and they made you do this. What is this? This is a specialty little card that does the same thing as that, except for the fact that this is guaranteed to work. In other words, it's a fault tolerant circuit. But this is a fault tolerant for just one device, and it's basically that device right there. So you feed it these signals in, and then it has an output that if they both hit within a certain period of time, then you will have an output that will allow the press to come down. Otherwise it won't. So this is a specialty card that would allow the same thing as that program. And this is the Schneider version of it. Siemens has a version of it. Allen Bradley has a version of it. These are discrete component fail-safe products, okay? Now this is what we had to use after we couldn't use this anymore, but before we had PLCs that were safe, all right? I programmed these and I programmed these, but I never programmed after that 2003 thing. But basically, what did we move on from here? We eventually moved to putting this function inside the PLC. So this function now can be put inside a program controller. It's called a safety relay for two-hand control stations, and that's what this does. So there's a safety right there, a function that went from being able to be programmed in a PLC to not being able to be programmed in a PLC, but in a specialty card, and then now finally being moved back into the PLC as a safety PLC. Okay. Anybody have any questions about that? By the way, why do they make you do this with the two hands when a press comes down? Why would that be an issue? How many people think it's dumb to put your hand in a press when the press is coming down? How many of you know why they make you do this? Why they make you do this? Any guesses? Well, this may gross you out, but it's the truth. All right? So, what do people do when they get bored? Dumb stuff, right? When you get bored, you do dumb stuff. So, instead of having to do this, what would they do if the press would be coming down? What would you do before they had the two hand switches? They would go into the press like that and then get their hands back out. No lie. That's why they, whatever. Does everybody follow what I just said? It's dumb, but it's the truth, okay? So now we have all this stuff. And anyway, now it sounds ridiculous, but I've actually talked to people that have done that. And if you don't believe that, I'll give you their names, okay? So that's the truth. That's what happens, all right? A lot of dumb stuff. Now, how do you create, or how do you grapple with something like this, okay? Well, I don't know, because I haven't done this. In reality, I have been teaching for long enough, and I've never done one of these systems in the real world. But I'll tell you how that they typically do this, and you can follow along if you want to, or you can just say, I'll do it my own way. But basically, if you are in Europe, you dial up what was called BGIA, now it's called IFA, and it's the German insurance industry responsible for setting up rules for plant safety or workplace safety. So basically what they've done is they've taken every situation, every scenario that they can possibly think of, and they've defined what it takes to make that safe. And by the way, can you make anything safe, perfectly safe? The answer is no. You can come close, but you cannot guarantee safety. But basically, why do people pay for this? Why do they pay for extra money for a safe system, or as safe as possible, knowing that you can't have perfect safety? All right? Why do they do this? Why does Ford, GM, and Chrysler and other companies pay so much money for safety? Because we're a litigious society. And if somebody loses a finger or a hand or an eye, what do? They sue. So what's your best defense? You've done everything possible that you possibly can to make it safe, and that's your defense. Now, maybe you don't think that's enough. Maybe you think that you can never be safe. But again, they've defined things that try to make it as safe as possible. And I can go through all this stuff. I want to show you another thing down here, and you may or may not believe this, but I'm jumping around a little bit, I know, but I want you to understand that. Okay, now this is an article from who? Who wrote this article? Siemens. Who's it about? Ellen Bradley. Losing $135 million in a lawsuit because a plant blew up, and what happened? Somebody got killed. 2 or 3 people got killed. It blamed an errant Ellen Bradley guidebook for installing switching equipment that malfunctioned and opened the gas line, which caused the explosion. Ellen Bradley contended that a short circuit from sewer water caused the malfunction and opened the gas line. It blamed the sewer problem and poorly trained KCP&L technicians who repaired the damage. Okay? Now, why, for instance, are there so many that you have to check from Allen Bradley? Some of the things that they do, like if you want to do an online change, you have to click and click and click and click and click to make that change. Do you say, do you want to do this? Do you really want to do this? Do you really, really, really want to do this? Why do they make you do that? Because of things like this. Okay? Because of things like this. And I'm not saying that these people did this. I'm not saying the people that sued are wrong. I'm not saying that at all. But I'm saying that the net effect of some of this is what you're seeing today is the software that you're using has a rationale behind it. Somebody wrote all that software, and the rationale is because of stuff like this. Something happened, and now they ask you to go through all kinds of links to make sure that what you program is what you want to program, or something to that effect. Okay. Now, all that said, that gives you an idea of the magnitude of some of the things that can actually happen. I want to go back and I want to show you, okay, some of this stuff. All right, so you're supposed to look at something and mitigate until you come to the conclusion that you've reduced the risk. In other words, now you're supposed to do this ahead of the process being completed. Okay, so you're supposed to do this times this equals this. I know, but on the other hand, you're also supposed to look at the machine directives and see if there is one like it, and you're supposed to copy that safety aspect. In other words, if there's supposed to be a guard on something, if that guard is supposed to have limit switches on it, if those limit switches are supposed to be redundant, all that is determined by these folk. So you don't have to think, you just basically find the example and copy it, and you're done. Now, sometimes you do not get the benefit of everything being done up front. And I'm going to say this, and I mean it, because I've been in this position before where you design something and then you have to go back after the fact and add something else into it, okay? So is it better to design with a safety PLC in your process and then discover after the fact that you definitely need a safety circuit that you didn't think you needed before? Or is it better to program a non-safety PLC, but then after the fact you discover that there needs to be a safety PLC, and you have to take out the PLC and put in another PLC that is a safety PLC? Which is better? Hedge your bets. Put in a safety PLC if you think there's even the remotest possibility of safety PLC being in your process. Do it up front. That way, if you need it, you got it. You don't have to go back and add it later, okay? And you cannot cross between the two. You cannot say, well, I'll just put in safety components after the fact. No, you have to put in the head. The PLC has to be a safety PLC from the get-go, okay? So therefore, that drives you to think of safety PLCs from the very beginning in most projects. Because if the possibility exists that you would have to put something in, even after the fact, even after you've put everything in that you thought you needed, but yet you discovered it after the fact you needed something else that was safety related, you have to go back and put it in, okay? It's up to you to do that. So the rub is always to put in safety and think about safety first. And that's why, believe it or not, that's why Siemens really got into the U.S. market, because people were not knowing what to do, so they just said, well, we'll just get Siemens to come in and do this. And they did. All right, now, how do they solve logic? How do they physically solve logic? Well, I'll see in a minute if I can show you how that's done. But here's a picture of the American and the European style of where safety is important. Okay, so in the United States, the line is right here, and between the United States and Europe, the line is right here between non-safety and safety. So right there. So category 2 is equal to SIL 1, and that's, you don't have to put a safety PLC. This is a regular PLC. But at this point, category 3 is equal to SIL 2. That means you have to have a safety PLC. And then SIL 3 and category 4 is a safety PLC plus power supply. It has to be a safety power supply. And I don't know what SIL 4 is. I really don't care. If you get into that, you look it up and figure it out. But basically, at this point in time, if you say it's a category 3 process, you must use a safety PLC. Okay? What determines this versus this is that BGIA manual and your boss. Somebody says this must be a safety PLC, therefore you buy it. Or you say it's got to be a safety PLC and you buy this one. Even though you may not use it fully as a safety PLC, you've at least hedged your bets. And that's what I probably would suggest. Unless you know that there's no reason for its safety, okay? Now, what does safety look like? Well, it looks like a double link chain. So every step of the way, you have 2 links, okay? Every step of the way, you have 2 links on the input, 2 links in the PLC program, and 2 links in the output. So that every part of this has if they have to agree, okay? So the inputs must agree. The program must agree. The outputs must agree. Or you shut it down. Any questions about that? Now, easy for the program, easy for the input and easy for the output. So you just double up. Everything is doubled, right? But the program is the one that's weird, okay? So, and I'm not sure what Allen Bradley does, but this is what Siemens does. They run the same program twice. Once positive logic, once negative logic, and they must disagree. Everybody follow that? I don't think so, right? And they say, how do they do that? Well, I can say, De Morgan, and you say, you nod a little bit, but you don't really nod because there's a lot of things that De Morgan didn't cover. De Morgan doesn't cover timers. De Morgan doesn't cover counters. De Morgan doesn't cover you name it. You follow what I'm saying? But they have a way to execute that even though it may not be covered totally by De Morgan. So if it's a straight logic, De Morgan will work. You follow me? If it's a straight ands and or logic, De Morgan will work. You do it positive, you do it negative. They got to disagree. If they don't disagree, you shut it down. But with timers and other things like that, you have more sophisticated logic. And honestly, I don't know how those work, but I do know that they do. Now, also, there is this aspect of it. The language of the safety circuit is much more limited than the overriding circuit language that you look at when you look at the ladder program. So you open up you open up all of the step 7 instructions. You don't have all of them. You just have a certain limited number of them, okay? And that's because not everything can be run positive and the opposite of or negative. You can't do everything. You can do some things, but you can't do it all. And that's the tip-off that some of this stuff can be done with positive and negative logic or whatever. Now, what does this do for you? It's the cheapest way to run a safety circuit, okay? It's the cheapest way to do it. You don't have to have two processors. One of the ways of doing this is to say, well, I've got two programs, right? I've got one that runs I want to run one in an Intel processor and one in a Motorola processor, or you pick, or a whatever. You pick the processors, and they both run the same program. And if they agree, then they're good. If they don't agree, then they're bad. Okay, now that sounds good, but that's not as effective as this approach right here, and it's double the cost. All right. So you see the rub? The Siemens approach really is kind of odd, but it does the trick, and it does it less expensively than anything else under the sun. And that's why they brag about it. It's so special. And like I said, I don't like saying that they're better, but they really thought this through, and they've done a good job of thinking it through. Now, again, I don't want to belabor one over the other, and I don't know the details. That's what I've been told. I've been through enough seminars that that's what they say. I kind of, yeah, okay, I nod, and but maybe it's not the truth. I don't know. Now, if you look at a processor and you see these yellow designations, that means it's a Siemens safety processor, or it's a Siemens safety IO, whatever. So this would be the processor. It's got the yellow, and here's the safety IO cards. Now, you can have non-safety IO cards attached to a safety PLC. You can use the regular cards that are not safe as well. And there's no reason not to do that, because you can have non-safety stuff running in the same processor as safety stuff. All right? Now, what's the rub there? You have to be able to have an interface between the safety and the non-safety portion. And you have to be able to pass data between the two. All right? You have to be able to pass data back and forth without corrupting the safety side. So there's rules for that as well. But it's doable. You can pass data between the non-safety side and the safety side. And you can also do what? In the safety side, you can also evoke these special functions that are, they're like sacred whatevers, but they work that process exactly. In other words, they're approved, they got the Good Housekeeping stamp of approval on them, and they do that function. So in other words, for the two-hand thing, there is a special function that does that. All you do is you configure some of the timers or whatever, but you can't touch the logic of it. You cannot go in there and change it if you wanted to. It's sealed. You can't undo it. You can't change the logic. You can maybe tweak a little bit here and a little bit there, but you cannot change the basic functionality of that block. It's sealed away from you. But you can get at the I/O of it. You can get at the inputs and the outputs, and that's what they want you to do. And then they want you to be able to take that data and then do stuff with it. Report, I'm down now, and I can do whatever, and I can do that. Okay, that's good. But you cannot change the basic functionality of that block. You can't do it. You can't unlock it. Same thing. This is Allen Bradley. So Siemens is yellow, Allen Bradley is red. Okay, but if you walk through a plant and you see this, it's a safety PLC from Allen Bradley. If you walk through a plant, this is safety PLC from Allen Bradley, from Monica, or from Siemens. Okay, red and yellow. Okay, we get back to our lawsuit. Okay. Now this is our safety circuit. What is it? Well, there's about 3 or 4 safeties. If you get them all set, then you can turn this on, and it'll actually turn on a motor. We don't have a physical motor, but it turns on a light. If you want to turn on a light, you can turn on a light. Now these are regular relays. My suggestion is that you do not use these. You use the little relays that you used before. And if you read down through here, it reiterates that. It actually tells you to use this relay instead of that one. And why? Because these relays have a push contact in them that only takes a size 18 or larger wire. And what size wire do you have in the lab? 22 gauge. It won't work. I've tried it many, many times, and it will not work. So take these 2 out, put these in, and away you go. These work just as well as these do. This is not safety. This is safety over here, but this is not safety. Okay? And there is one wired, and it worked. It works. And there's the wiring instructions of how it works. There's the wiring directions of how it works. And I have to give credit where credit is due. I did not do this the first time through. There was a fellow that was a student here that did it, and he got it to work. And I think I give him credit for it someplace. I think I named him, put his name in here. Anyway, I'm forgetting it right now, but I'll remember it as soon as I walk out of here. But he was very good, and he was the first person to get this to work. And I copied it, took the wires off one by one, copied it, and put it in here. And this is the program, and we actually had the program already done, pretty much. And he finished it off and got it to wired, and he got it to work. You do not have to write the program. The program is written and downloadable. All you have to do is wire it. But in so doing, you're going to learn an awful lot about how this subject is, what it does and how it works. Okay? I told you this before, but one of the outputs is a category 4 output. The others are category 3. What's the difference is the power supply. And there's a power supply in there that actually has a pulse in it. And if you wire it to a regular power supply, it will not work. It only works with its own power supply. If you wire it according to the drawing right here, it will work. Any questions about this program? Austin was his, I forget his name. Austin something. But he did it. He got it working. Learned a heck of a lot too. We all did. Okay, so this is another, some videos, that type of thing. And there's some more videos from Real Powers on safety. And done. This is how that circuit works, by the way. Most of the circuits work this way. This picture shows the two programs working, the two inputs working, and the outputs working, and the outputs have feedback. Both of them have a feedback that they're working. Austin, I forget his last name. And this is a safety lab that we started with that we then converted to the one we actually have. This was not the one in our lab, but this is close. So I went to a vendor show, stole all this stuff, bought the 8. And by the way, the price goes up quite a lot. I mean, it's not like 10 times more, but it's like 2 or 3 times more for a safety PLC than for the regular PLC. So there is more money in them for the people that are buying this, for the people who are selling them. But this gives you some labels and stuff of how it's set up. So if you're interested in making a safety PLC work, this is from a vendor seminar that I went to. But the wiring for the one we have is pretty straightforward, and it does the job. And I welcome anybody that wants to do this wiring diagram. And that's all it is this right here. That's it. But it's a bear to get to work. Every wire has to be exactly right. It has to be tightened down. It has to be exactly what it. It's very unforgiving. And use this relay instead of that one. But you can do that. Any questions anybody's got? Because this is an invitation to There's 8 of these, and you can do this at your leisure. Okay? Anybody have any questions in general? So tonight we opened up a whole new can of worms, or whatever you want to call it, the safety side. And again, I don't want to oversimplify it, but I do want you to understand that you do have to face the idea of safety. Whether you're mechanical or electrical or whoever you are, whatever you're up to, you have to face it, and you have to look at it and try to solve how to create a system that is safe as best you can. And if you have no clue, you're going to be swimming around for a while. But on the other hand, now you have some places to turn to and some questions to ask and some people to actually be able to ask some questions of. My suggestion is to turn to that BGIA book and start looking there and start asking questions and see how you do. But do not say that you have to do everything ahead of time. You have to do what you can do ahead of time. But after the fact, if you still see safety issues, if you have a safety PLC, you can confront them and you can actually program them in. If you don't have a safety PLC, you're dead in the water. You can't do it. You have to have a safety PLC to program safety items. Everybody understand that? You have to have all the 3 parts, the inputs, the program, and the outputs all working together. You can't say, well, this has got safety because I have dual inputs. No, it's not. It has to be dual inputs, dual processors, and dual outputs. It has to be in a safety PLC in order to make it work. One more thing and I'll be done. There's a handoff procedure in this realm, and it's a very litigious procedure. So what you do is you get your program up and running, and you create a password for your program, then you lock it in, okay? Then it's not able to be unlocked unless you have that password. And nobody but you can do that. Now, when you go and you give this to a customer, or when you pass it off to a customer, you have to get them to sign off that they are receiving the passwords to be able to change it. Everybody understand that? Because if you don't, if they make changes to it, if you give them the password and they make changes to it, then you're still the one in charge of it. You basically allowed them to undercut you and do things that would cause you to be sued. So there is a legal aspect of this as well as the programming aspect of it, in that you pass them at some point in time. It's like passing the baton. You pass them the passwords, and now they're legally responsible for making changes to that program. You have to be able to do that in a legal way with signage and all that kind of stuff. You just can't say, okay, you can have the password now. Nope, you do not do that. Nor do you give them the passwords. You have to make them sign off that they had taken those passwords, and then they are the people who are in charge of it. They carry the baton from that point on. You have to do that. Make you lawyers, right? Make you all lawyers. Okay? Any questions about that? Take care. We'll see you. See you Wednesday. Did everybody get that around, passed around? Thank you. Thank you. If you didn't pass in those things earlier, I'll take them now. Thank you. I know I'm going to have fun grading those.